Hi! We're so excited you want to learn more about the JADES survey using our amazing Fitsmap website. With Fitsmap, you can explore tens of thousands of galaxies stretching back to some of the earliest ones we've ever seen. My name is Kevin Hainline, and I'm a professor at the University of Arizona and a member of the JADES NearCam team. We've all worked incredibly hard to bring this amazing data set to you, and we hope that you enjoy looking at these distant galaxies as much as we have. In this video, I want to walk you through the basic functionality of Fitsmap so that you can understand what you're looking at and how to learn more about individual sources you see. So let's get going. This here behind me is the public version of Fitsmap right as you load it up. Fitsmap is a tool that works similar to many online maps you've used before, but instead of looking down at streets and roads, we're looking up at the JADES Deep region of the sky. The Fitsmap software was developed by Ryan Housen and Brant Robertson, two other members of the JADES team. And if you want to learn more about how Fitsmap was developed or how it works, there's a link you can click right below me in the bottom right corner. This large rectangle here is the JADES Deep region. And to give you an idea of how big it is, it's only about a fourth the width of the moon on the sky. It's actually a larger, more extended, and deeper view of the very famous Hubble Ultra Deep Field, if you're familiar with that image. It would just be a box that would be nestled within this much larger JADES field. So let's zoom in. You can zoom in by clicking on the plus and minus up in the top left corner. So you see, I click in plus and minus, or you can just scroll with the trackpad on your mouse. As we zoom in, you'll notice there's a lot of objects. Almost everything that you can see in this image is a distant galaxy. There are some stars too, but this image tells us that the universe is just full of galaxies, and they're all unique. You can click and drag to move around this image and look at everything. Up in the left-hand corner, you can also click this little information box to learn more about JADES and the Fitsmap image. The gear icon that's below it allows you to change some of the color settings in the image. So you see I can change the brightness or the contrast. And by double-clicking on the slider, you can reset it back to its default settings. So what you're looking at here is a color mosaic that's made by combining three individual mosaics in filters that we've assigned to be red, green, and blue. We'll talk about what that means in a second, but you should know that JWST is an infrared telescope, so it looks at infrared light that's outside of what we can see with our eyes. The camera that took these images that you see here is called NearCam, and it operates at a wavelength range between 0.7 and 5 microns, which we call the near infrared. We had to take this infrared light and color it, so using optical colors to present it here. And this image represents hundreds of hours of observations. So if you were floating in space, looking out at the universe, this is not what our eyes would see. To get an image like this, you would need a very, very big infrared telescope like JWST. So let's get into what we're offering here with Fitsmap. Up in the right-hand corner are two buttons, very important. The top one shows different versions of the data, either different color combinations of filters or the individual filters themselves, or layers that show how we selected galaxies. If we click it, we can see that the layer we're looking at is composed of three images. You can see them here. The red you're seeing comes from an image that JWST NearCam took using a filter that's 4 microns. The green comes from a filter that's at 2 microns, and the blue comes from a filter that's at 0.9 microns. But if you click on another set of these buttons, you'll see another filter combination. Now the red you're seeing comes from an image at longer wavelengths. If I click on this filter, the red comes from an image taken at 2.8 microns. The green comes from a filter at 2 microns, and the blue comes from a filter at 1.2 microns. So if I zoom in, you can see that galaxies look a lot different when you use different filter combinations. Astronomers use these different combinations to explore different aspects of the objects in space that they're looking at, like how dusty they are, or what types of gas they have, or just how far away they might be. This second option here presents an image that uses multiple filters combined to create a color map. The third option uses data using NIRCam's long wavelength filter, and the galaxies really look different at these longer wavelengths. Below this color options, we list the individual filters that are in the JADES dataset, one by one. Most of them cover the whole region. Like if I look at this one at 0.9 microns, it covers the whole region here. But some of them, like this one here at 1.8 microns, only covers part of the region because of how it was taken from another observational program called GEMS that we combined with the JADES data. If we click on 0.9 microns and look at this object like, say, up here, we can see how it looks at different wavelengths, 0.9 microns, 1.5, 2.0, all the way to 4.4 microns. It looks like a spiral at longer wavelengths, but it really is hard to see that it's a spiral at 0.9 microns. This is because it's a giant spiral galaxy that's pretty dusty. There are other objects like this that you can't even see until you get to longer wavelength filters. We'll come to some of those a little bit later. So let's zoom out now. Notice when I look at this that there are gaps in the coverage. Well, it turns out these gaps are because of how we take the data with JADES. JADES is combining a lot of smaller images to make what we call a mosaic, and the coverage is not completely closed for every single one of them. At the long wavelengths, if we look at a long wavelength image like 4.4, you see that we actually get coverage because of how NIRCam works. But at short wavelengths, that's not the case. There are gaps in the coverage. We show that because on Fitsmap here, because it's actually how we take this type of astronomical observation. Real astronomical data has these sorts of gaps. And that's part of the excitement of doing science. So now that we're zoomed out, we can click on another cool image here. If we go down below all the filters, we see that it says detection image. If I click on that, you can see a pretty amazing thing. This is what happens when you combine almost all of the data together at every filter to get an incredibly deep view of the universe. This image is what we actually used to find the individual galaxies. If you zoom in like I have now, you can see just how many galaxies there are everywhere between all the other galaxies. The universe is truly filled with galaxies. Remember, these galaxies can have hundreds of thousands or millions or billions or even hundreds of billions of stars in them. Zooming out, we used this image here, our co-added detection image, to create what's called the segmentation map, which is our image that shows how we parceled off everything into individual galaxies. All of the colored dots that you see here are the individual sources in the catalog we've produced from these data. There's almost 50,000 galaxies and stars. It's kind of fun to go back and forth between this image and the detection image to really see that we've pretty much got everything. Let's do that again here. Detection and segmentation. So now that I've introduced you to how we found all of these galaxies, what if we wanted to know more about one? What if we went back to, say, our color image and we looked into here and we said, man, I would really love to know more about something like this galaxy right here. Well, that's where the second button up in the top right corner comes into play. If you click this, you'll see that we have overlays that are generated to help you explore the galaxies in more detail. The first one, JADES NIRCam catalog, puts ovals around the objects in our catalog. If you click on the circle surrounding the object, like this one, you'll get a huge amount of information, like its ID number, its position on the sky, which we call right ascension, RA, and declination, or DEC, some information about the shape of this oval, how it's rotated, and how bright it is in all of our filters, which we measure in a very small unit called a nanojansky, or NGJY. It's not that important exactly how bright a nanojansky is right now, but it's very helpful for scientists who want to understand these objects. If we turn that layer off, and we turn on the second layer here, JADES NIRCam SEDs, you can see another way of looking at these sources. Here, we just plot a small circle over all the sources in each image. But if we click on one of these circles, like this one, you see a box pop up that has less information data-wise, but a big set of charts. These charts show the object's SED and a fit to that SED. SED stands for spectral energy distribution. It's a very fancy way for scientists to just show how bright a galaxy is at different wavelengths. So this top left box right here, that box, all the colored circles shows how bright it is in all of the filters that we have, combined with the filters in Hubble Space Telescope, which we color kind of pinkish, versus the red here, which are just the JWST JADES filters. The blue line that connects all these dots, that's a model fit to all of the data points. And we use that to calculate the distance to this galaxy. We provide that in the upper left corner here, where it says ZA. This galaxy is modeled to be at a redshift of 0.29, so it's kind of in our backyard. And for this object, a more careful analysis has shown that it's actually at a redshift of 0.337, which is pretty close to the prediction. The number ZA then is a predicted redshift just based on looking at the images themselves. We only have a confirmed value, this Z-spec value, for a handful of the objects in this image, maybe 1,400 objects, and mostly just the bright ones. And if we have that, we include that in these plots as Z-spec. So most of the redshifts that you'll see, which is our distance of the galaxy, are just an estimate based on looking at the images that go in to this object. On the right's kind of a complicated plot that tells us how well we believe the blue line fit to the observations, and we don't need to worry about that much right now. Below, however, is a kind of fun thing where we show what this object looks like in all of the filters that we have data. The Hubble filters, F435, F606, F775, F814, and F850, are the first 5 here, and the rest are JWST NIRCam ones. Each picture shows the name of the filter, which gives you a kind of rough estimate of the wavelength, and a number underneath, which is the signal-to-noise ratio, or SNR. And it's essentially how bright the light is that we measure compared with how noisy our estimate is of the brightness. A higher number means that the galaxy was really well detected. So you can see that for some of these, our signal-noise ratio is like 800, really great signal to a low noise level, versus maybe the faintest one, which is this F435, which is only detected at a signal-noise ratio of about 30. So let's use this knowledge to look at an interesting object that I know is pretty fun right here. So let's click on this source right here. Again, we'll go back down and put JADES NIRCam SEDs and click on it. If we click on it, we see that the redshift of this object from our fit is 3.68, and the blue line goes through the points pretty well. The confirmed redshift is 3.723, and the object is special because we know that the confirmed redshift is here. You can see we don't actually see it in the F435W filter. That filter is represented here in this pink, and it's pretty faint. What's also cool is that if we go and drop the SEDs and click this box here, a yellow circle will appear. This box says JADES NIRSpec Spectra. One of the other instruments that's on JWST is called NIRSpec, and JADES has used a NIRSpec to look at a number of objects like this object here. If I go and drop this box and click on it, you see something very special. NIRSpec is a spectrograph. It takes the light from distant galaxies and spreads its light out by wavelength into what we call a spectrum. Here you can see the spectrum, this bright yellow line that we represent above with this thin blue line. The taller the line, the higher up it is, the brighter the light at that wavelength. Notice there are these big bright spikes. Spikes from hydrogen, spikes from oxygen, spikes from nitrogen gas, glowing 9 billion years ago when we're seeing this galaxy. And by looking at where those spikes are, this spike here is about 2.4 microns, and comparing that number, 2.4 microns, to what we would measure if this galaxy weren't hurtling away in an expanding universe, which is about 0.5 microns, we can measure the redshift of this object, which is 3.723, the number you see right here. So going back again to the NIRCam prediction, you see how we know. We know this galaxy is at 3.723 because we have the spectrum that you can see from the JADES team. And I did pretty well with 3.68, the NIRCam prediction. While we're here, we can turn on the fact, we can look at there's these things that JADES near spec pointing, 7, 8, 13. If I click on those, you can see these boxes show up. And if I click on 13, you see a set of boxes. This is how we actually pointed near spec at this object. We open these little boxes so that we can really focus on the light from this galaxy specifically to spread it out into a spectrum. Near spec has let us see some very, very far away galaxies. So let's go find one. If I back out a little bit and kind of scan over, we can zoom in on this one, which has some boxes over it. Right here, I'll turn the boxes off. And we click on it, and we see that this object right here, the NIRCam image says that it might be at a redshift of 10.82, but it's pretty faint. The signal noise ratio is only 6 or 4 or 7. It turns out, though, this object was confirmed at a redshift of 10.409, which we can see again from looking at the spectrum for this source. Really faint, but this tells us that the galaxy is at 10.409. It's one of the farthest galaxies that humans have ever confirmed. So all of this together is an enormous data set, and that's kind of it for Fitsmap right now. We've also created a Fitsmap that's primarily for the scientific community, but it mostly just has a lot more complicated layers that are helpful for understanding the complicated details of the data set. We want you to have a great time looking at these data and these beautiful images. This is an incredible way of zooming in on interesting things in the distant universe and then going and being able to click and say, what's actually going on in these objects? This red one, what is it going on? It looks like it's at redshift 2.9. Pretty amazing. If you want to know more about the JADES project, you can click on this information and go over to the JADES collaboration website at jades-survey.github.io, and you can read about the team and our publications. If this video has been helpful, please leave a comment, like, and hopefully you subscribe to our channel for more JADES science. My name is Kevin Hainline. I'm so excited that you're going to be looking at JADES data because this is a work of love from many, many, many people. There's more JADES data to come in the future, but for right now, you got 50,000 objects to take a look at. I hope you have a great time. Thank you so much.